Well, I would like to begin by thanking Sigma Xi for inviting me to speak, and particularly Professor Laktakia for inviting me here. He asked that I speak about structural color in minerals. And it's true that over the past 2.5 decades, I have devoted a lot of my research interest to the subject of iridescence in minerals, but I've never really pulled all of these separate projects together in a single talk. And so it was fun for me to prepare this talk, and I hope it's of interest to you. So coloration is profoundly important in the animal kingdom. Sometimes we know the reasons for coloration, sometimes we don't. In many cases, animals have colored body parts as part of their mating rituals. Here you see a photograph of a bird of paradise. It turns out there's a dance that accompanies the bright display of colored feathers in the choice of mates. Other times, animals use color as warning signals. Frogs will often have brightly colored backs in oranges and reds to indicate that there are toxins in the skin, and so predators should not even think about eating them. Parrots exhibit a very wide display of colored feathers, and ornithologists are not even sure why this is the case. There's some speculation that it just has to do with a parrot being able to identify another member of its tribe. And of course, coloration plays a very important role in camouflage. So many times animals try to camouflage themselves to prevent being eaten by predators. In this case, there's a yellow spider from Thailand that is trying to blend in with a flower petal so that it will lure in unsuspecting flies that can't distinguish it from the background. Humans, of course, also embrace coloration. We spend $25 billion per year on pigments, and we color things ranging from paints to inks to plastics, cosmetics, and food. And it goes deep into human history. I'm sure you're all familiar with the Lascaux cave in France. These are paintings that date 20,000 to 30,000 years ago. The yellow browns are pigmented by goethite, FeOOH. The reds pigmented by hematite, Fe2O3. And Homo sapiens is not the first hominid to be using ochres for pigmentation. A recent paper that appeared in Science revealed stenciled handprints on a cave in Spain. And the researchers were able to determine definitively that these hand stencils were made by Neanderthal because there was a mineral overgrowth on top of the hand stencils. So therefore post-dating the hand stencils, and they were dated to 66,000 years ago. At that time, Neanderthal was the only hominid in Spain. And so this artistic impulse is not unique to Homo sapiens sapiens. And then a group out of the Smithsonian made a discovery of ochre being applied to tools from 300,000 years ago in a cave in Kenya. So these archaeologists actually found pieces of ochre and various kinds of tools that had been stone tools that had been colored by ochre. They could not even speculate what the type of hominid is that inhabited the cave. But obviously, this desire to color things, it goes deep into our history. So mineral pigments operate through the selective absorption of wavelengths of light. On the left here, you see a schematic representation of the atomic structure of hematite. And it turns out that there are electronic transitions that absorb over particular frequencies, and so therefore allow other frequencies to pass through the crystal. This is an absorption spectrum for hematite obtained by George Rossman, a mineralogist at Caltech, who has devoted much of his life to causes of coloration in minerals. And what you can see is that these electronic transitions in hematite absorb very strongly in the violets through the yellows, but there's a window in the reds of transparency, and so that allows the hematite to appear reddish to our eyes. But there are drawbacks to pigmentation as a mechanism for color. The major drawback is that many pigments fade upon time, and typically the culprit in that fading is ultraviolet light. So UV rays from the sun, they can actually force the ejection of an electron from a bond, and they thereby disrupt that absorption mechanism. And so that leads to bleaching of the pigment. Animals have come up with other mechanisms for pigmentation. There are some animals that use pigmentation. Flamingos, for example, are colored pink because of pigments, and goldfinches are also colored yellow because of pigments. But there are other animals in the, that use what is known as structural color. So when you look at the butterfly wings of Iridescent, you might see, well, there are reds and oranges here, probably indicating some kind of an iron containing chromophore, but in fact, that is not what is responsible for the coloration. When one zooms in on these wings, butterfly wings with a scanning electron microscope, in fact, you see that there is a substructure that's present of chitin platelets that are ordered in space with a very high periodicity. And they actually serve as a diffraction or scattering grating for visible light, and certain wavelengths are reinforced and others are not, as I'll describe in a moment. In addition to butterfly wings, fish scales show the same kind of structural color. Lots of insects have carapaces that show structural color. Even the feathers of a peacock show this amazing structural coloration. And the beauty of structural color is that it does not fade or bleach upon prolonged exposure to ultraviolet radiation. And there's a kind of intensity to structural color that one does not observe associated with pigmented color. In the case of the peacock, we have multiple colors, greens, browns, and blues, and it all is based upon the substructures within the feathers, melanin rods embedded within a keratin layer. It turns out even chameleons engage in this kind of structural coloration. And the way that they change their color is basically by transforming from a relaxed state to an excited state that changes the lattice configuration of these greeny nanocrystals that are embedded in two layers of their skin. And so by changing the structure of these greeny nanocrystals, that will actually change the color that is diffracted by the chameleons. So studying these kinds of structural coloration mechanisms in animals is an important part of the field of biomimetics, which means applying engineering, chemistry, and biology to the synthesis of materials that mimic biological properties. So on the right, you actually see a figure from a relatively recent paper where some researchers were examining substructures in the wing of a morpho butterfly, which appears blue. And it turns out this is a structural coloration mechanism. And so they use polymeric synthesis techniques to try to kind of build the same types of structures that would also generate a blue structural color. And I wanted to give a shout out to a professor at Penn State who also was involved in understanding structural color, but working with liquids rather than solids. Lauren Zarzar is a professor in the chemistry department, and she has looked at microdroplet emulsions where one can tune the colors that are scattered off of these liquid emulsions. So at its foundation, this kind of structural color is always the result of a kind of a simple phenomenon known as wave interference. If we drop two pebbles in water next to each other, concentric circular wave fronts will emanate out from the points where they drop into the water. And where we see waves, peaks that are interfering with each other, they're going to create a taller wave. Where there are troughs interfering, that's going to create kind of a weaker trough. And then in addition, where there is a peak that is interfering with a trough, they're going to cancel each other out completely. And so these are illustrations of constructive and destructive interference. We have two waves that are completely in phase with each other. Then those two waves are going to sum their amplitudes. And that's significant because the intensity of a wave is typically the square of the amplitude of the wave. And so in the opposite case, where we have two waves that are completely phase shifted by 180 degrees, so they're completely out of phase, well, the peaks and the troughs are going to cancel each other, and we end up with what's known as total destructive interference. So we can illustrate how structural color works just by thinking of a thin film on some kind of a substrate. If incident light intersects this boundary right here between the air and the film. Some of that is going to reflect off of the film surface, but other components of this ray are going to penetrate the film, and then they're going to reflect off the interface with the substrate. There's going to be a little bending of the light due to refraction, but the point is that if it happens that the peaks of the emergent light waves, number 1 and 2, are lined up with each other, we expect to see total constructive interference. And if they're out of phase, then they're going to destructively interfere. And so there are 4 parameters that we worry about in trying to model this kind of thin film iridescence. One is the angle at which the light ray is going to be reflecting off of the film. Another is this wavelength, the distance from crest to crest, known as lambda. A third is just the thickness of the film. And then finally, we have to take into account the refractive index of the film. And so one can put it together using some high school trigonometry and demonstrate that this product here, 2 times the refractive index times the thickness of the film times the sine of the reflection angle, in order to achieve total constructive interference, all of that has to equal some integral multiple of the wavelength. When that condition is met, then we expect to see total constructive interference, and when it's not, it's going to achieve destructive interference. So that's kind of illustrated in this animation that I purloined from the web, showing waves of a constant wavelength, lambda is not changing, interfering with a lattice with a constant d spacing, so the d is not changing. The only thing that's changing is the reflection angle right now. And you'll notice that there are moments when all of the peaks align at a particular angle, and we get that total constructive interference, but at all other wavelengths, everything's going to cancel out, and it's destructive interference. And so this is really underlying the basis for structural color. We can see the dependence of that scattering angle in these 2 photographs of the same mallard duck at different angles. So on the left, the head looks green to us, and on the right, it looks blue. The blue is at a lower angle, and so it's selectively, we're seeing selective total constructive interference of the shorter blue wavelengths, but at a higher angle, it's the green wavelengths that that interfere totally in a constructive fashion. And gem dealers have taken advantage of this behavior by spraying crystals of quartz with very thin films of titanium metal in order to generate this kind of thin film iridescence. And so this takes a lackluster group of clear quartz crystals that might sell for just $10 or so. And by applying this thin film of titanium, you can achieve this iridescent effect that they call flame aura quartz and cost a lot more money. In fact, my mother-in-law really loved the flame aura quartz pendant that we bought her. She wore it all the time. Kind of a related situation is when instead of a thin film on a substrate, you just have periodic gratings. It turns out that the mathematical formalism is identical to what happens when you have a thin film. So a CD-ROM is like the perfect example. The information in a CD-ROM is encoded through pits with an aluminum layer. And so those rays of light that are going to reflect off of the aluminum will have to interfere in a totally constructive fashion with those rays of light that are reflecting off the bottoms of the pits in order to achieve a certain kind of color. And so it's the same n lambda equals 2d sine theta formulation. And that's why the backside of CD-ROM shows that beautiful rainbow effect. At low angles, we're seeing the greens and the blues, and at higher angles, where's my arrow, the greens and the blues, and at higher angles, we're seeing the reds and the yellows. This is a structural color mechanism. And of course, one can also think not just of a single thin film, but we can actually layer many thin films, if you will, on top of one another, and also achieve this kind of structural coloration. Nacre, or mother of pearl, is really the best example of this. Many different kinds of clamshells actually consist of thin layers of a calcium carbonate called aragonite, and they are glued together by a combination of proteins and polysaccharides, and they have a very, very consistent thickness to these platelets. they're transparent at this thickness. And so light rays are actually reflecting off of each one of these layers. And again, it's just this lambda equals 2d sine theta kind of formulation that gives rise to iridescence. And as a result, pearls have a kind of iridescence, and abalone shells do as well. And of course, the classic example of an iridescent substructure would be opal. Opal is the national gemstone in Australia. In the 1950s, some mineralogists decided that it was time for them to really understand why opals exhibit opalescence, which is iridescence in opal. And so Dara and Sanders, P.J. Dara, J.D. Sanders, they used this newfangled instrument called a scanning electron microscope to examine the substructure of opals. And to their surprise, what they discovered was that at very high magnifications, the opal consists of these little beads of silica. The silica is amorphous, it's non-crystalline. It's also a little bit hydrated. And the beads typically measure about 1/10 of a micron to up to 10 microns in diameter. And that's just the sweet spot for generating an interference pattern with visible light, because visible light wavelengths are a little less than a micron. And so these little beads of silica are packed together in a geometrically ordered kind of way. Often one sees a closest packed kind of arrangement within opals. And so now we're seeing not just like a two-dimensional type of layering, but we're seeing kind of a macrocrystallinity in 3 dimensions. And so these are often called 3-dimensional photonic crystals. And opals have inspired an enormous number of materials that engineers have tried to create based upon this opaline sublattice. They don't just use silica, although it's possible for us to simulate opal with silica. But these kinds of opaline kinds of lattices have been created with all different kinds of chemical systems. And this then becomes an example of geomimetics. Instead of using structural color in animals as inspiration for material, we think about minerals as providing us inspiration for structures. And why geomimetics? You know, why do I feel, having studied these things for 2.5 decades, why am I so intrigued by geomimetics? And I think there are reasons that geomimetics actually has advantages over biomimetics. One is that, you know, when engineers are trying to simulate a biological structure, they can successfully reproduce the substructure, but they don't do it in the way that the butterfly does it. They're not actually kind of creating a butterfly. Only God can really create the butterfly. And so they're not really mimicking the assembly process itself. They're looking at the structure, and then using other techniques, they can create that kind of structure. These biosynthetic pathways are extremely complicated and hard to replicate. But geological materials, they're forming in the earth. They tend to be much simpler, things that we can actually reproduce in a laboratory. Another factor is durability. You know, what is more emblematic of fragility than a butterfly wing? Geomaterials, on the other hand, are highly durable. Opals are found in rocks that date between 25 and 30 million years in age in Australia. Opals are actually considered among the more fragile gem materials because they're a little soft, 5 out of 10 on the most hardness scale, and they're susceptible to losing water. But nevertheless, you know, opals are infinitely more durable than insect wings or insect carapaces or fish scales. And so geomaterials have advantages over a lot of biomaterials in that respect. And then finally, you know, as a geochemist, I'm really interested in the processes by which these repetitive structures at the nanoscale are formed. I think that gives us deep insights into dynamical geochemical processes that we don't understand. And so by characterizing these materials, we may be able to have a new insight into geochemistry. So today what I wanted to do was to describe 4 geomaterials that I have investigated over my career. And they include hematite, iridescent hematite, which is Fe2O3. This is an example of a material that normally we don't think of as a gem at all, but when it's iridescent, jewelers actually pair it with high-end gems like sapphires and tourmalines, as you can see in that ring. Goethite is normally considered to be rust, orange yellow, not very pretty to look at, but in fact, there are certain kinds of goethite that have this brilliant coloration. Prismatic quartz crystals normally are just transparent, but in certain localities, we see iridescent reflections off of the faces of quartz. And so we'll explore that. And then finally, we'll talk about iris agates, which have really intricate substructures. But we'll begin with iridescent hematite. Iridescent hematite is actually found in many parts of the world, but some of the most spectacular localities are in the Quadrilateral Ferrífero, which is an iron mine in Brazil. It's actually located in the state of Minas Gerais, just a little bit north of Rio de Janeiro. And it was brought to the attention of gem dealers in America in the 1990s by Rock Currier, who was a famed kind of mineral collector and mineral dealer, passed away just a couple of years ago. But he observed that there was this very sparkly iridescent hematite that was interbedded with what's called a banded iron formation in Brazil. This banded iron formation consists of layers of jasper. Jasper is fine-grained quartz mixed with fine-grained hematite and magnetite, and that alternates with bands of just of hematite. And since they formed 2.3 to 2.5 billion years ago, there's a big opportunity for them to metamorphose over time. And so the material that we're looking at here is actually a hematite schist. You don't find this very frequently in the United States, but there are localities where you can actually metamorphose a banded iron formation to make this kind of sparkly hematite schist. And the iridescence is quite striking. In fact, I brought some samples up at the table for those of you who want to take a look at these objects at the end of the lecture. The locals knew about this iridescent hematite, made use of it. They would often grind it up before a holy day. And I guess there are many holy days in the Brazilian calendar. And so on these holy days, there would be parades through the streets, and the locals would sprinkle the streets with these hematite dusts. And Rock Currier said it was like walking through peacock feathers, as all of this sparkly dust would be kicked up as people walked through it. The first efforts to study the causes of iridescence in hematite were done by Chima and George Rossman, again at Caltech. In the 1990s, they analyzed this material with a scanning electron microscope, and they saw this striking pattern of spindle-shaped crystals oriented at 120-degree angles relative to each other. And they observed that there was an aluminum and phosphorus signal in their energy dispersive spectroscopy analyses. And they inferred that they were looking at some kind of aluminum phosphate mineral that had never been described before. But significantly, they were never able to generate like an X-ray diffraction pattern or a Raman spectrum for this material. And so they never actually published this. This has been on their website for the past 20 plus years. So some years ago, a student from the China University of Geosciences came to me from the gemology program, Xiaoyang Sunny Lin, and I suggested to Sunny that this iridescent hematite might make for a good project. So we obtained some of this material, again, from that same locality, the Andrade mine in Brazil, and a low magnification in the scanning electron microscope. It doesn't look very exciting at all. This looks like kind of your regular hematite crystal, but you got to zoom in to see this texture that George Rossman and Chima had described. And in order to see it more clearly, Sunny used the atomic force microscope in the Penn State Materials Characterization Laboratory and achieved this striking photo, which was on my poster for this talk. And so what you see here are these little spindles, again, oriented at 120 degrees from each other. The lengths of the spindles are usually on the order of 200 to 400 nanometers. The width is much less, about 30 to 40 nanometers in size. So we did our own energy dispersive spectroscopy, and we did indeed find evidence for the aluminum and phosphorus that George and Chi had described earlier. But I was familiar with the fact that in hematite, the most common substituting impurity is aluminum for iron. And so we said, well, what if this is just getting incorporated into the hematite structure, and these are indeed just hematite nanocrystals? we do that, we can generate a formula that's not quite Fe2O3. It's what you see right here. Yep, with aluminum and phosphorus substituting for the iron. And then independently, we collected some synchrotron X-ray diffraction data from this material. And we used a technique that's called Rietveld analysis to see whether, in fact, aluminum was substituting into the iron position. And there was really no doubt as we were doing our crystallographic refinements that aluminum had to be substituting for iron. And when we did our refinements, we found the occupancies where 89% of these certain sites were iron and 11% were aluminum. And in order to compare our X-ray diffraction results with the microprobe results, you just have to double the numbers that you see of these occupancy. So the ALOCC there is 0.11 times 2, that would be 0.22. And that's a pretty good match for what we found with the energy dispersive X-ray spectroscopy. And the iron, likewise, when we double it, it matches very closely to what we got from this EDS data. So in other words, there's really very little doubt that in fact, these little spindles are hematite that contain iron, aluminum, and phosphorus impurities. And in fact, material scientists have synthesized hematite, and they found that when phosphorus concentrations are high, they poison certain surface sites. And so instead of growing as flat hexagonal platelets, which is how hematite normally likes to grow, it will instead adopt the spindle structure. Now, the next stage is that these spindles attach to each other. And this process was popularized in the late 1990s by Penn and Joe Banfield, who described it as oriented aggregation. And the idea here is that iron has got a threefold symmetry. So there's kind of energetically three equivalent orientations that these spindles can adopt as they attach to each other. And so what ends up happening is that you generate this kind of substructure, which we consider to be the iron oxide analog to opal. Instead of spheres that are micron scale and nesting together, instead we have these kind of nanometer sized spindles that are aligning themselves in a crystallographically ordered way. The difference is, again, that the opal is amorphous, it's non-crystalline, but these actually are crystals of hematite that have stacked on top of one another. And they generate a diffraction grating as a result in the same way that opal does. So, okay, now let's turn to another member of the iron oxide family, this kind of iridescent goethite. Collectors call this turgite. And the question we asked ourselves is, is iridescent goethite another one of these kind of three-dimensional nanocrystals, a photonic crystal? When we look at the surface of the turgite, you'll see it's very bumpy and has kind of a cauliflower appearance. Mineralogists have a name for this. We call it a botryoidal structure, meaning a grape-like kind of structure. And so we're going to zoom in on this turgite specimen using scanning electron microscopy. And here's what we see at high magnification, that just like a cauliflower having this kind of self-similarity, we see this hummocky structure at the nanoscale as well. We're going to zoom in even more. We begin to see some substructure within those little hummocks and even more. And I think I have one more here. And this reveals to us that the goethite is growing by oriented aggregation as well. We see these linear fibers on the surface, but they're segmented. I think of them as kind of like sausages that are all attached to each other. And we weren't too surprised because Penn, who's at the University of Minnesota and has published a lot of papers in oriented aggregation, she's done much of her work in the goethite system. And so she's shown really conclusively that goethite often grows through this oriented aggregation process. So my first reaction was, okay, we've got a diffraction grating here. We see these kinds of parallel lineations. But then I looked at the scale bar and I realized that the spacing between these lineations was far too small to account for any kind of iridescence. It's on the order of 20 nanometers or so, and that's much too small to create an interference grating for visible light. So I had to think about other possibilities. And when I was examining these kinds of turgite specimens, one thing that really struck me was that there was a texture here that looked a lot like thin film interference. And in particular, what I noticed is that one saw many orders of interference. Rainbows we think of as being consisting of this Roy G. Biv coloration. And we can see many iterations of these, here we go, these kind of Roy G. Biv sequences here. And when we see these successive iterations, that might remind you a lot of what happens when you drop some oil onto water, and you can see successive sequences that are Roy G. Biv colors here. And the reason for this has to do with the change in thickness of that oil film, and that allows us to sample different kind of values for N, and that N lambda equals 2D sine theta law that I described earlier. And so when that happens, we can see many different kind of orders of constructive interference. So the question is whether essentially we're looking at some kind of a thin film effect with these tergite specimens, and that meant I needed to cross-section through the tergite. So I went to the materials characterization lab here, and Trevor Clark and Kay Wong were particularly helpful for me in extracting a focused ion beam section through this material. And so when we looked at this, this is actually an ion beam image of one of these sections. I didn't really notice a thin film per se, because everything that you see here is goethite, the mineral goethite. But what we always observed in all of our colored specimens was that there were layers of vacancies underneath the surface and fairly close to the surface of the specimen. But what was interesting was that these vacancies are not strictly periodic in the way that they are arranged. They're kind of quasi-periodic. Now, that actually made sense to me, because if you have a strictly periodic stacking sequence, then you get a very strong angular dependence. Just like opal, you change the angle of opal relative to your eye and different colors flash out. But when we're dealing with this tergite, it's the same color no matter how you tilt the tergite. And that is often kind of consistent with a quasi-periodic stacking sequence that kind of destroys that angle dependence. So I then collaborated with Tobias Wenzel. At the time, he was a postdoc at the University of Oxford, and he specializes in these quasi-periodic interference effects. And I said, Tobias, if I send you some of our images, would you be able to reconstruct the color that one might observe? And so on the left here, upper right, is the original image that I sent to Tobias, and then he kind of color inverted it. And this is actually the reflection spectrum that came out of his analysis. And then the question is, well, how does the human eye perceive this reflection spectrum here? And he has another computer program that allows him to sum all of this together. And it turns out this is the final color that he simulated. And the chip on this SEM stub that we were going after was that. I'm sorry I don't have a better picture of it, but I think you can kind of see that is a greenish color. And so in fact, his analysis matched what we expected to see. And so we became convinced that indeed it was these void layers that were serving as kind of reflectors and are responsible for this iridescence that we see in this spectacularly covered tergite. So here's a specimen from my own collection from Thorsis, Spain. And we decided let's take some thin sections from two adjacent colored bands. As you can see arrowed here, we have a violet band close to a blue-green band. I was curious to know, is there a difference in these void layers? And at first I thought the answer was no, until I put the two micrographs right next to each other. And on the left is the section that's taken from the violet part of this tergite, and on the right is a section taken from this blue-green portion. And you'll notice, kind of fortuitously, we have two void layers that match up exactly, but this last layer right here is displaced by 150 nanometers. So again, it's just like that oil film on the water, that we're changing the thickness of the film, and that is allowing us to access different colors in the interference that we see. These void layers can be very baroque in their appearance. Sometimes there's more void than there is goethite, and yet you still see this spectacular iridescence from these kinds of chips. And what we don't really understand is what is responsible for the void layer. And I haven't actually published because I've been mulling this for 2 or 3 years, longer than I really should. But I think what I've finally concluded is that these are probably the result of surface poisoning. My reading is that these tergite specimens, they form in room temperature iron-rich muds. And so collectors go into these localities that are very muddy, and the nodules are actually growing within the mud, and they collect these nodules, and then they have to wash them off, and they hope that they're iridescent on the surface. So there probably are wet and dry cycles, and during these dry cycles, the growth of these nodules ceases. And what often happens is that kind of contaminants fall on the particle surfaces. Let's see if I can get my arrow here. And they essentially poison these surfaces right here. And then if there's another episode of rain, and so further growth of the iron oxyhydroxide, only some of these crystals are really going to be compatible with additional growth. And so we end up with this kind of a void layer. And so that right now is my best guess as to what's responsible for the growth of these voids. Another possibility is that we know when these nanoparticles are coalescing, they have to be releasing water. And so I've also wondered whether there isn't an inclusion of water during the buildup of these successive layers as they grow. That might be a part of the story as well. Okay, so let's now jump to the silica system from the iron system and consider these iridescent quartz crystals that are overall, just clear, transparent, prismatic quartz, but some faces show some really beautiful iridescence. What's interesting about this prismatic quartz is that not all of the faces of the quartz are iridescent. In fact, crystallographers have letters that we use to denote the different faces in a prismatic quartz crystal. The sides are known as the M faces, and there's usually on the terminal face, there's one big face that's known as the R face, and then there are these smaller Z faces. And it turns out that the iridescence is always restricted just to these Z faces. So let's talk a little bit about the background of these crystals. They form in these cavities that are associated with basalts, massive basalts in India. And these massive basalts are known as the Deccan Traps. And these particular crystals come from West Central India. And the way they grow is that basalts are extruded in this massive extrusive process that we don't completely understand. And as they cool, there's a lot of outgassing of water, carbon dioxide. The basalts actually harden and they trap these gas bubbles within the basalt. And then at a later stage, some silica-rich waters, they percolate through and they begin to deposit quartz on the insides of these cavities. And so these quartz crystals are growing to the interior of the cavities. These iridescent quartz crystals were actually first discovered by a British engineer who was associated with a railroad construction in central India. And he saw these iridescent quartz crystals and sent them to the British Museum as examples. And they actually still have their samples of iridescent quartz. So anyway, people had just assumed, well, there probably was some kind of organic film that got deposited on these crystal surfaces, and we're just really looking at like a thin film of oil or something, and that's what's responsible for the coloration. But interestingly, there was another scientist who thought otherwise, C.V. Raman, the person who discovered Raman spectroscopy, and he actually studied these quartz crystals and came to the conclusion that the iridescence was caused by a stratified medium consisting of a great many parallel layers of extreme thinness, but he wasn't quite sure what physically that meant. And so we're going to see whether C.V. Raman got his physics right. So Sunny Lin, again, my graduate student in gemology, decided to look at these prismatic quartz crystals with a scanning electron microscope. And on the left, what you're looking at is that boundary between an iridescent face and a non-iridescent face. And very consistently, the non-iridescent faces are just flat, but the iridescent faces actually show this kind of ridge and valley texture. And when we zoom in at higher magnifications, this kind of diffraction grading within the crystal becomes immediately apparent. So as soon as we saw this texture, we know immediately this had to be responsible for the iridescence. Sunny took her samples again to the materials characterization laboratory, looked at them with atomic force microscopy, and kind of reproduced what we saw with the SEM. We have this ridge and valley texture on the iridescent Z faces, but there's no iridescence on the R faces. And so this texture that we see right here is called a blazed diffraction grating. And the mathematics for this kind of constructive interference of the blazed diffraction grating, it's a little bit more complicated than just a thin film, but nevertheless, it's worked out. And still, there's kind of angle dependence to the color that is reinforced selectively. The distance on average between these blaze peaks was calculated by Sunny statistically, and she found it was something like 350 nanometers or so. Again, right in that sweet spot for visible light interference effects. So we wanted to understand what was responsible for the blaze diffraction grating on this quartz crystal. And again, we did some focused ion beam analyses where we dug a trench into one of these ridge faces right here, and extracted a sample for analysis by transmission electron microscopy. So now again, we're looking at this face in cross-section, and you will see, if I can find my arrow, this blazed diffraction grating, which is fairly periodic here. And when we look at it in cross-section, we find boundaries that are separating these layers. The C-axis of the quartz crystal is indicated as follows. And I have a lot of experience in working with quartz, and I knew immediately that this had to be a certain type of what is called a twin of quartz, known as a Brazil twin. So what are these Brazil twins of quartz? Quartz is the formula silicon dioxide, SiO2. Every silicon atom is surrounded by 4 oxygens, and they create kind of a tetrahedron, and the tetrahedra are linked together in helices. Well, the helix can have one of 2 senses. It can spiral away from the eyeball in a counterclockwise fashion. That's known as a left-handed screw. And if your eyeball looked at this from the top or from the bottom, you'd find that it's spiraling away from your eyeball in a left-handed or counterclockwise sense. On the other hand, we could have spirals that spiral in a clockwise sense as you look down on them from either the top or the bottom. And so that is called a right-handed screw. Just to clarify it even more, we can compare it to the horns on a ram. So here is the crystal structure for right-handed quartz. And it turns out that there are 2 intertwined chains of silica tetrahedra. And in this case, these chains are spiraling away from your eyeball into the screen in a clockwise fashion. And so that's called a right-handed kind of screw, just like the horn on the right side of this ram's head, spiraling away from your eye. But conversely, on the left-handed side, spiraling away in a counterclockwise fashion. And we can see that's happening with this tetrahedral spiral, and there's another tetrahedral spiral right here that's doing it. And quartz consists of these 2 helices that are spiraling next to or with each other in a way that's analogous to DNA. But the difference is that every organism on Earth, from the lowliest bacterium to a human being, we all have right-handed DNA. In quartz, on the other hand, it is thermodynamically equally probable to crystallize left-handed or right-handed quartz. And so we find not only left-handed crystals and right-handed crystals, but within the same crystal, we see left and right-handed quartz intergrowing with each other. And that's what we call the Brazil twin of quartz. And so it turns out, these Brazil twins are accommodating strain. The strain can be induced just by squeezing a crystal. We can actually make Brazil twins by squeezing on it. Or if there are impurities that are, in a sense, creating strain from within, because the impurity elements have a different size than silicon does, then Brazil twins can also be generated. And that strain field gets released, in a sense, by the generation of these Brazil twin boundaries, which are kind of storing the strain energy. And so they are very regularly spaced. And those impurities that might be responsible for the creation of the Brazil twins, they tend to diffuse. And once they get to the Brazil twin boundary, it's a very hospitable environment, and they stay there and they twin that boundary. So what we observed then is that in these Z faces of the quartz crystals that are iridescent, there are these polysynthetic Brazil twins that are lined up with a periodicity that's exactly right for the diffraction or scattering of visible light. Now, there has to be a final stage here. because C.V. Raman himself was thinking maybe Brazil twinning is possible here. But the problem is that Brazil twins themselves are not going to lead to iridescent effects because they have the same refraction index. You have to do something that's going to make the light kind of reflect. And it turns out the second stage here must have been a hydrothermal alteration, that some fluids percolated through the cavities in which these quartz crystals were contained. And those fluids etched away the surfaces and even were able to eat along the Brazil twin boundaries themselves. So these boundaries that we're seeing here, they're not really beautiful Brazil twin boundaries. They're really boundaries with lots of little fluid inclusions left over from this etching event. And once that happened, now you have the conditions for the kind of reflection and constructive interference that will lead to diffraction. So now finally, we're going to talk about the most complicated iridescent mineral of all, iris agate. And the story of iris agate is in some ways analogous to the prismatic quartz crystal I just talked about, because agates form in a similar way to these prismatic quartz crystals. They typically form within empty cavities of host rocks. They might be basalts that have released bubbles, or they might be sedimentary rocks that have got voids in them. But if there are silica-rich solutions that are percolating through those cavities, the silica-rich solutions begin to nucleate quartz crystals in the cavities. And the difference here is that when agates form, there is this kind of very, very fine-grained, here we go, this very, very fine-grained quartz that gets deposited first, and then there's some kind of a change that results in the deposition of the more coarse-grained kind of prismatic quartz. We call it a quartz druze in geology. Now, in some cases, this chalcedony is very, very regularly banded. And so we have to ask ourselves, what is the difference between chalcedony and rock crystal quartz? Because they both have the same formula, it's silicon dioxide. But obviously there's some kind of a difference between the two. And as I've already kind of hinted, it has to do with crystal size and crystal texture. So here's another cross-section of an agate. And it turns out that this agate, if you looked at it at very high magnification, it actually consists of radiating fibers of nanocrystalline quartz, and those radiating fibers are also twisted. So you can't see the crystals with the naked eye as you can with the quartz druze. If I can find my arrow, this right here is this coarse crystal druze, macroscopic quartz crystals, but this fine stuff right here, this is all made up of these fibers which are radiating inward. I often think like spokes on a bicycle wheel. So here's the proof of that, scanning electron microscope image of these chalcedony fibers. This is an agate that I etched with hydrofluoric acid, following a recipe that Clifford Trondell, who was a mineralogist at Harvard in the 1940s through 80s, and he was the one who suggested you could bring out the textures by etching with hydrofluoric acid. And so when we do that, we see the fibrosity really clearly. There are fibers radiating from the lower left towards the upper right of this micrograph here. And if you look closely, you'll see that individual fibers are actually spiraling around, kind of like a barber pole. Here's one right here that I like a lot. Okay, you can see that spiraling fiber. And even though you might think, well, here's like maybe a single crystal of quartz, in fact, these are made up of nanocrystals of quartz. We're not seeing the individual crystals in the scanning electron microscope image. So as these quartz fibers grow, they generate this very regular banding. And it was not clear when I started this project what was responsible for that regular banding. But what was really striking is that the regular banding could actually diffract light or create these kinds of rainbow interference colors. So I stole a little video from the Asia Gem Incorporated website. They're trying to sell these iris agates for $99 per section. It's actually a pretty good price. And these are spectacular iris agates, as you can see. And one thing, just go back and restart it again. If you focus on a given band, you'll see the angle dependence. Notice how this is blue, then it's orange, blue is an orange. Just the coloration just depends upon that angle between the incident light and the agate itself. So iris agate can be really, really spectacular. When we look at an iris agate with a petrographic microscope, just a light optical microscope, we actually see fringes that are associated with this iris banding really clearly. You see them here as these vertical striations, and the distance between these striations is on the order of half a micron to maybe a couple of microns or so. And they've been documented to repeat up to 17,000 times in a single specimen. When we sort of back off with the SEM to kind of see this texture in an etched agate, you'll note again this kind of hill and valley in the etched agate. We don't see this in a kind of a regular thin section agate. I have to etch it with hydrofluoric acid in order to see this texture. But what it reveals is that there's kind of a bimodality to the chalcedony. Some chalcedony is very susceptible to etching, and some of the chalcedony is very resistant to the etching. And there is kind of a strict periodicity to the bands that are susceptible and the bands that are very resistant. And this was where Clifford Trondell wasn't really sure what was responsible for that differential etching behavior. But I examined these with this, transmission electron microscopy. Back in the 90s, we're kind of going into some of my ancient history. And what I found was that, you know, this TEM micrograph answered a lot of questions. To you guys, it might look like a Jackson Pollock painting in blacks and whites and grays. But if you squint your eyes, I think that you can see that there's actually kind of a vertical striation. And again, there's a bimodality we can pick out. So what you might notice, for example, here is a layer that is very, very fine grained, but is attached to this layer where you can actually make out the individual crystals. They're not huge by most people's standards, you know, 1/10 of a micron. If you're a microscopist, you kind of get the feeling that that's a big number, but that's succeeded by some really, really fine grained stuff that's like 10, 20 nanometers or so in size. And then we have kind of a more coarser grained zone, a fine grained zone, a coarser grained zone. And this is what explains the differential etching, because these very fine grained crystals, they have a lot of surface area. They etch very rapidly in hydrofluoric acid. Those coarser crystals, they are resistant, and so they don't etch so quickly. And then I don't want to get too technical here, but I did some electron diffraction work on these fine-grained and coarser-grained bands. And just to show you, with the electron microscope, I can collect what's called an electron diffraction pattern. And this array of spots here corresponds to this crystal that you'll see right here. And the appearance of these spots is actually the result of the same kind of constructive and destructive interference effects I've been talking about with respect to color, but now we're getting close to the atomic scale. And what I really want you to note is the arrangement of spots in this diffraction pattern here. When we compare the primary spots in a diffraction pattern taken from this modeled stuff, it's the same. And so what that tells me is that the crystallographic orientation of all of these thousands and millions of nanocrystals within this modeled region here, the crystallographic orientation is identical to the crystallographic orientation of this coarse-grained crystal. But what I noticed is that there are streaks that are running along these rows. And that is a sign that we have, again, this pervasive intergrowth of left and right-handed quartz. So in other words, intense Brazil twinning here. We can't see the Brazil twin boundaries. They're way beyond the resolution of this particular instrument. But nevertheless, we know we have a lot of this Brazil twinning in the fine-grained regions. And so kind of schematically, what we inferred is that there are shifts, some areas where there's a very regular change in handedness from left to right, from left to right, from left to right. And then there are other areas that are all primarily left-handed or right-handed, with this maybe the occasional Brazil twin boundary. And this model was actually confirmed just a few years later by Huifeng Zhu. He's a friend of mine. He's a mineralogy professor at the University of Wisconsin, who used a very high magnification TEM to get high resolution images of chalcedony, and showed indeed, where you see these white bars, again, where's my arrow? These white bars here are Brazil twin boundaries. And so this is essentially Brazil twinning at the atomic scale. And so we've got these regions that are densely Brazil twinned, alternating with regions that are not very densely Brazil twinned, just as we had inferred from our X-ray diffraction data. So that almost atomic scale micrograph is outlined by this red box that you see on my TEM image here at lower magnification. And in this image, you see coarse-grained quartz crystals, fine-grained quartz crystals, coarse-grained quartz crystals, fine-grained quartz crystals. And so that kind of alternation between dense Brazil twins, less dense Brazil twins, that's all embedded within this fine-grained region that you see here. Now what we're going to, so this is the iris banding, by the way. So this is the banding that is separated by a couple microns and scatters light and produces that beautiful iris effect. We're going to step back again in magnification. And that image that you just saw taken with the transmission electron microscope corresponds to this red box that's right here. We see that now embedded within a light optical microscope picture. And I'll just tell you that this region right here is fine-grained chalcedony, and you'll notice that's alternating with coarse-grained quartz. And this fine-grained chalcedony is intensively Brazil twinned. We don't have Brazil twinning in the coarse-grained quartz. And it repeats again, fine-grained Brazil twinned chalcedony alternating with coarse-grained quartz without Brazil twins. And again, we see this repeat, chalcedony that is intensively Brazil twinned, transforming to coarse-grained quartz. And now let's step back and actually look at the agate. The last three micrographs were taken from the same sample here. And so that last micrograph came from this region right here of a Brazilian agate from the Smithsonian collection. And again, we can say, well, this is all chalcedony. Oops, sorry. This is all chalcedony and this is coarse-grained quartz. And so again, we've got this transition from intensively Brazil twin material to this non-Brazil twin, highly crystalline material. And so in essence, what we're thinking about is like Russian dolls with respect to crystal textures. We see the same kind of alternation between intensive Brazil twinning alternating with less Brazil twinning at 4 different scales. And so this kind of embedded texture is very reminiscent of a pattern known as a Cantor dust. So George Cantor was a mathematician in the middle of the 19th century. He's kind of the founder, one of the founders of set theory, and he loved diabolical sets. And so he loved playing with this set that is generated by, you start with a solid bar and you remove in step number 1, the middle third of that bar. And then you move to the next stage and you remove the middle third of these bars. And then in the next set, you remove the middle thirds and just keep doing this infinitely. And what you end up with is this pattern that is kind of fractionally dimensional, right? A point is 0, has 0 dimension, a line is 1 dimension, plane 2. And this Cantor dust that we end up with, it's not fully aligned, so it's less than dimension 1, but it's more than just a single point. And so he was wondering, how do you kind of describe that? And it wasn't really until the 1980s and the rise of fractal geometry that people were able to handle that in a quantitative fashion. But my point is that these agates actually kind of are a mineralogical manifestation of these Cantor dusts. The Cantor dust has a self-similarity. We can take a subset of the Cantor dust and it looks just like the original parent pattern. We can take another subset and that looks just like the parent pattern, and we do it again and we do it again. And of course, if we continue this infinitely, we could just do it over and over. And so these iris agates, they blow my mind because they are, in a sense, Cantor dusts with respect to Brazil twin densities. So if we begin with like pure chalcedony, where we think at the atomic scale, we just have left, right, left, right, left, right alternations at the unit cell scale. And then in the next iteration, we decide to remove all of the Brazil twin boundaries. So we have a segment that is purely left-handed or purely right-handed. It looks like this. Let's do it again to the remaining segments right here. And so now we have a segment that's pure left-handed, another that's purely left-handed, and we do it. This is essentially the pattern that is observed within these iris agates. And so these iris bands that give rise to the iridescence, they're fascinating, but in fact, they're just a single subgroup of what is really a 4th order Cantor dust within these agates. We don't know how agates form, really. It's one of the surprising things that we can synthesize almost any gem material these days. No one has ever synthesized an agate, and people are still debating fiercely how agates form in nature. And so what I can't do is postulate formation mechanism for these iris agates. So what I can say, though, is that the mechanism that we see in agates is different from the iridescence mechanisms in these other minerals. Iridescence in geomaterials is diverse just the way it is with biomaterials. We've talked about a 3D photonic crystal and hematite, quasi-periodic void layers giving rise to the color in goethite, these blazed gratings from etched Brazil twins of prismatic quartz, and finally these crazy hierarchical oscillations in Brazil twin defect densities in agates. So I think this is a field that is still like underexplored. There are a lot of other iridescent minerals, a lot of things for us to discover still. I can't stop without making some acknowledgments. Sunny Lin did all of the work on the turgite, no, not the turgite, I did that, on the prismatic quartz and on the iridescent hematite, and C. Athena Chen helped me with some of the work on the turgite. I've never really had any grant that funded this work. It kind of is leached off of other grants that I have obtained in the past. And I want to, of course, acknowledge all the folks at the Materials Characterization Laboratory, particularly in my case, Trevor Clark and Kay Wong, who assisted me in the use of the instrumentation there. So with that, I'll leave you with this quotation from Langston Hughes: "O God of dust and rainbows, help us to see that without the dust, the rainbow would not be." I love this relationship between the Cantor dust and the iris agate, and I'm happy to take questions from you.
Questions?
Sure.
A very naive one, comment is I've always wondered the science behind how people were able to take, for example, a gemstone and be able to source exactly where it was from and date it.
Okay.
I've always wondered about the science behind it. This talk kind of brought that in mind.
Yeah, you know, the answer is going to be different for different gemstones, but scientists use whatever they can grab onto in order to figure out where a gemstone formed, how it formed, and when it formed. So, for example, people can look for impurity inclusions within certain gemstones. Emeralds always grow with impurities. They actually create defect fields that are called jardin, which is the French word for garden, because a natural emerald always has got inclusions. And it turns out that those included minerals can help you determine whether it's an emerald from Chivor in Colombia or Egypt or India. Also, there are gemologists who've started looking at isotopes. You can look at oxygen isotope ratios, for example, as a way of fingerprinting minerals from where they come. So it's a challenge. You know, every mineral system is going to be different. I can't really give you a general answer except to say that we will grab every piece of chemical, structural, impurity data that we can to try to make some kind of a map of where a gemstone formed. Yeah.
A more generalized question that's based on that. So when we watch NCIS and we used to see Abby pick up from somebody's shoes stuff, and then
Yeah.
she would end up saying, okay, this is at this location in an area
Yes.
because of whatever it does.
Yeah.
Is that realistic?
Yeah, so that's when I turned off NCIS. I watched it in the early days, and there was exactly that episode that someone had quartz crystals that were embedded in their shoes, and then they irradiated the quartz crystals with an ultraviolet light, and mysteriously the quartz was fluorescing, which never happens. And then they were able to determine, oh, this quartz must come from this locality. So yes, in a certain way, it is true. I know the FBI, that there's Smithsonian scientists who collaborate with folks at the FBI in order to do that kind of provenancing. But it's a very, very inexact science because many minerals, they really look very similar from different localities. And quartz in particular, you know, it's one of the most common minerals on the earth. And so therefore, trying to source quartz is virtually impossible. it's too universal. There has to be some really odd inclusion within the quartz, some very rare mineral that is only found in one locality, and then you might be able to say, oh, this quartz comes from this place.
But it does make for really good TV.
It does make good TV, I guess, because NCIS certainly, despite my disapproval and shutting off the TV, it continued just to get more and more popular over time.
They're still ongoing, although, she's gone, Abby's gone.
Abby's gone.
A
Okay.
replacement. I wanted to make a comment here at the beginning when you were talking about, carrots and whatnot, two different things.
Yeah.
We have had carrots for many years.
Oh,
Not anymore, unfortunately, but, our first child, was a cockatiel. And actually, one time when I took him to the vet, she pulled out, a UV lamp
oh,
and
Oh.
the light,
oh,
the UV light,
oh.
and showed us what his bed looked like.
No kidding.
And it was amazing.
Isn't that
Because
interesting?
all of a sudden this, so I think it was not with Simon, Hill, it was with Rusty. Rusty was a normal gray cockatiel, so his head was gray, and he had the bright orange cheeks. And all of a sudden, it was just colorful.
And so can birds sense ultraviolet rate? They can see into the ultraviolet?
Yeah.
Birds do have.
I did not know that.
Um,
That's amazing.
Not only that.
Birds and also some butterflies have.
Really? Okay, I had no idea.
The other example of cool stuff with birds was with Peter. You can probably describe it better. Peter was an Indian redneck, Becky,
Huh.
but she was mutation. She was yellow instead of being just your normal green with the reddish neck. She was this striking, bright yellow, and I can show you a picture because I was looking for it. And of course, I interacted with her a lot. And many times I could see like the difference. She was not yellow, she was green.
Huh.
But, you know, when I told my husband, he was like, really crazy. No way, because she was so bright green,
Uh-huh.
bright yellow,
Right, yeah.
and she turned green.
Huh.
And you can probably explain it, but I'll show everybody a picture of how yellow she was.
Huh.
But, and that was structural.
Okay.
Anyway, go around and show.
Should I maybe stop the recording here? No?
Here, we can continue talking and recording.
Right. But the problem is people can't really hear, and so I think maybe I'll stop the recording. There we go.